me great pleasure to introduce Dale Freed. The reason it's a particular pleasure is that a teacher is always delighted when a student goes on to a creative and useful career, and this is exactly what Dale has done. He worked with my research group to get a PhD, and then went to Lincoln Labs for some years, and eventually left to start up his own company based on Lidar mapping. So I thought this would be of interest to all of you. So let me just introduce Dale. The floor is yours.
Thank you. Thank you, Dan. That's a kind introduction. Thanks for having me today. I'm going to talk about a kind of LiDAR that I was privileged to work on at MIT Lincoln Laboratory, and then to continue on in this company that I started to commercialize it. And hopefully everyone will find something interesting about this. What I find interesting is that we are detecting and time-stamping single photons and then trying to learn as much as we can from every single one of those photons. And I'll show you how that works and some of the data products that come out of it. My focus is on mostly on systems that go in aircraft. So that's kind of fun. We get to go fly in airplanes. Usually with the door closed, so that's good. This is a picture here of one of our systems inside of a twin-engine turboprop aircraft that was here locally in Norwood, Mass, where our company is headquartered. And these are some of my colleagues that I get to work with on a daily basis. It's a real privilege to work with talented people, as I'm sure you all know. In general, what I'll be talking through today is, first of all, an overview of LiDAR in general, very quick, and then we will get into this special kind of LiDAR that works with single photons called Geiger-Mode LiDAR, and we'll start with the receiver side. Think of like a radar system where you have a transmitter and a receiver and beam forming and all that sort of thing. So we'll start with the receiver, because that's the thing that's particular to this kind of LiDAR that makes them so, in my mind, intriguing. Then I'll talk about a few systems that I have been involved in building and that my company has brought to the market and brings to the market. That's the practical side. Then we'll go back into the signal processing, which in some ways is really kind of the second half. It's great to collect lots of photons, but what do you do with them, and how do you make a 3D survey data out of those collected photons? So we'll talk a little bit about that, and then kind of summarize at the end with some applications. Why is this kind of LiDAR particularly interesting? My hope is that everyone will find something interesting to take away, whether you've never heard of LiDAR ever before, or you've done a lot of work in the field. So there will be some things about optics and computing and aircraft and mapping and all that sort of thing. This is an area of interest, especially in the DoD world. And you can see logos from sponsors who've been involved along the way. It's also of interest in the commercial world. And so I've got some logos from some different mapping companies. MIT Lincoln Lab has played an important leadership role in both the components that are used, as well as the system technology and data processing technology. There's companies that have commercialized and make some of the components that we buy and put into our systems. All right, so first we're going to start with what is LiDAR in general. So the idea is that you start with a pulsed laser. This is for direct detection LiDAR. There are other kinds of LiDAR for the specialists out there. But we send a short pulse down to the ground. These pulses in thickness are, 20 centimeters or so thick. A half a nanosecond to a nanosecond type of pulse widths. And think of that as a flashlight that we illuminate the ground from an aircraft up in the sky. Some of the light bounces back from different points on the ground and comes back into an aperture, a telescope, and that focuses onto a detector. Traditional LiDARs typically have one detector. One of the things that's kind of cool about these that I'll get into more is we use a whole focal plane array, a camera, effectively of pixels. And each one of those pixels is special. It measures time. When did that photon arrive? Or in the more traditional LiDAR, when did that pulse of light arrive? So by comparing the time of flight, the time between when the laser pulse went out and when we detect the time of arrival, knowing the speed of light, we can work out the distance. So we have which pixel it is, which is the angle that we're looking, and the distance. So angle, range, that's three-dimensional information. We combine that with knowledge of the position and the orientation of this telescope and any scanning that we have in there, and we're able to put a dot in three-dimensional space, latitude, longitude, and elevation. And we do that millions and millions of times, and we come up with a point cloud that's geolocated. And by that, I mean we know the absolute latitude and longitude and elevation for each of those points. And this is just some example data. This is actually from Afghanistan and some really rugged terrain there showing the shape of that. So you can actually go in and do measurements in there. Okay, that's basically how it works. To put it in context, other sensor systems that go on airplanes often are electro-optic systems or camera systems, optical systems. And yes, this is like that in the sense that we have resolutions of those kinds of systems, maybe something on the order of 30 centimeters or a foot from 20,000 foot elevation or 6 kilometer elevation. But we also have range information that's of the same sort of resolution as what you get from radar. So again, something like on the order of 20 centimeters from these long standoff distances. So that's great. We kind of combine the best of both imaging modalities, radar and optical. Another advantage of LiDAR systems is we are providing our own illumination. We're not depending on the sun being at a certain angle or whatever. We bring along our own illumination, so we can do this at night or during the day, both, either time. Obviously, there are disadvantages compared to these other modalities. One is we cannot see through clouds. It's optical, so it really does require a clear line of sight. And also, the active illumination can also be a disadvantage. There's limited amount of power that we can apply to the problem, and that results in a limited rate at which we can go and collect data. So a limited area collection rate. That's the overview of how LiDAR in general works. And I'll give you a couple pictures of the kinds of data products that you can get from this. So this is an example collection over the Grand Canyon. This is part of a much bigger collection. But you see here we're color-coded by elevation. And you can see, you know, red up at the top of the south rim, all the way down to blue, down by the Colorado River. It's a lot of vertical relief, and this kind of information allows us to go in and precisely measure slopes, where you might be able to walk, where trails are. Water drainage, obviously, is a big application of this sort of thing. A few specifics: this product resolution in this particular example is 1 meter, and the area collection rate is 300 square kilometers per hour. So an air. This system that collected this data is called ALERT. It was a test bed system that we were working with at MIT Lincoln Laboratory. There's some specifics there. This system actually went to Afghanistan over a 4-year period. It mapped about 2/3 of the country. We joke that country is better mapped than many parts of the US. Here's another example of a follow-on system that's a little bit more capable, again, just to give you a sense of what this data is sort of like. This is looking down at the city of Boston, and the data here is processed to a better resolution. This is 10 to 20 centimeter type of resolution. This was flying a little bit lower. It was a better system, and this system went into South America and served for the DoD down there for many years. I'll show you a video. If we zoom in here, each of those dots, of course, is a point in three-dimensional space. So we can now take this just like a CAD model and move it around. You can see the Zakim Bridge there. You see the outlines of the buildings. Every dot on here is a place where we were able to do a measurement. So things like glass that are really shiny and specular, we don't tend to get good measurements off of those, but things that give us a diffuse reflection, dirt, roads, wood, trees, all those sort of things, allow us to make these very highly detailed maps of large urban areas. One more example here. Those were urban areas where it's open, you can see in. But another big application for LiDAR is looking through those small openings in the forest canopy. There's always a few small openings, and if you can poke down through those, you can kind of see what's on the ground underneath. So this is a movie of data we collected. This is about a 3-minute collection covering a circle about 1 kilometer in diameter. Under which there's various roads and trails. And this is a picture of me actually walking down one of the trails in this area. This is in Puerto Rico. So I will play this movie now and show you how this all works. So you can see there's terrain. Clearly there's a river bottom down there. That's the blue, that's the low elevation. It's a very rugged scene and it's very highly foliated, a lot of trees, very dense canopy. However, as I said, some of the light does make it down through the canopy to the undergrowth and the ground underneath. And so people have put together algorithms to try to estimate most reliably where that ground actually is. Once you have an estimate of the ground, you're now able to trim off or digitally defoliate, sometimes we say, all that tree canopy to reveal what's on the ground. And in this case, there's this narrow winding road. There's a trail or a smaller road that goes off of that. There's some trails through the area and so on. Coloring of the data is a powerful tool you can use to highlight things. So we'll next go and color by height above that estimate of where the ground is. So in this color bar, we've cropped and we're coloring from slightly below the ground estimate to a little bit above. And you can see in this area here, oh, by the way, this is covered by an awful lot of foliage. Let's just keep that clear. It's highly foliated area, but I can see under that foliage where there's bushes as well as some man-made objects. And in this particular case, these brown points here are some pieces of plywood that we put out as test targets to see if we could see them, to demonstrate, the visibility of those targets. And that was to mimic, clandestine human activity that might occur out in the jungles and isolated areas. So you can understand why there's a lot of applications that like to use LiDAR data, whether it's forestry, wide area mapping, looking through foliage, lots of applications. Okay, so that's an overview of what LiDAR is and why people find it useful. Now let's move on and talk about the single photon technology and in particular how that works. So I'll walk you through the story here. As I said, these LiDAR receivers, Geiger-Mode LiDAR receivers, detect and timestamp individual photons. Now, there's a few different technologies for doing that kind of single photon detection. Geiger-Mode is what I know about. There's Mercad telluride APDs, there's microchannel plate detectors, nanowire arrays, and so on. There's lots of different technologies, and they have their strengths and weaknesses. I'm talking today about Geiger-Mode avalanche photodiode arrays. And kind of where I'm headed in my description here is to say that we're able to detect and timestamp somewhere between 100 million and 1 billion photons per second over these imager arrays. Those arrays have thousands to tens of thousands of pixels. So how is the magic done? Here's a picture that is courtesy of MIT Lincoln Laboratory, who has done a lot of path-leading development on these. Here's a picture of a packaged array. So inside of here is a small focal plane array. In this case, this is a 32 by 128 array. And just kind of zooming in with a cartoon here, there's all these avalanche photodiodes spread out. Each one of those avalanche photodiodes is a mesa structure with an absorber region and a multiplier region. The light comes in here from the back. It's back illuminated, so it comes in, gets absorbed There's a high voltage, a high field gradient here, or a high field, sorry, a voltage gradient across this area. And so you can get this runaway avalanche effect. The idea here is that you can take a regular photodiode and there's a breakdown voltage. But if you bias that photodiode slightly above that, a volt or two above that breakdown voltage, it doesn't actually break down immediately. It breaks down when there's a tunneling event or when there's a photon that excites a carrier. So in that short amount of time, which can be on the order of microseconds, you can actually have it above the breakdown, biased above the breakdown voltage. And then when you have one of these events, you see a volt level drop. And if you see my pointer over here, I'm plotting the bias voltage. We over bias it for some amount of time measured in microseconds. And then you have a volt level drop of that voltage, which can trigger a standard CMOS logic circuit. So attached to this point in the circuit is a readout integrated circuit that contains these CMOS timing circuits. So that's shown up here. And these circuits are small enough to put behind each pixel in this big array. So that means that coming out, instead of reading out your camera, as most cameras do, where you have intensity for each pixel, we read out time for each pixel. So there's a few, really compelling advantages of these devices. Single photon sensitivity, as I said. It's noiseless readout in the sense of the act of reading doesn't add read noise into the readout. You're just measuring time, really. You're not measuring intensity. It turns out that the bandwidth on these circuits can be quite high, so that we have half nanosecond timing resolution, and some research groups have done substantially better than that. And because we can fit that timing circuit behind every pixel, you can scale these up to quite large arrays. MIT Lincoln Lab is up to 128 by 256 arrays. And in the commercial world, one manufacturer, Ball Aerospace, now BAE Systems, sells a camera. And it was the presence on the commercial market of these cameras, which was kind of the triggering event that allowed me to leave and start this company, which has been a great adventure. So they will sell you different size cameras with different specs. But typically a frame rate, just to put a real number here, 90 kilohertz type of frame rates for those 32 by 128 arrays is typical. Okay, let's move on. So how would we apply this to an actual condition? So think about being in an airplane. We send a laser beam down through, let's just say there's a tree. There's some tree branches up high, maybe medium, down low, and then you have the ground. So what would the signal look like coming back from that? So I put together a little toy model of what this is like, and I tried to show at different heights here how much cross-section I would have, or how much light would be coming back. And you can imagine kind of a column of light coming down, and there's branches that intersect it. Different area of branch corresponds to different size of this little lollipop here, or different amount of light coming back. When we send the beam down, some of the light comes back from up high, some medium, and there's hopefully a little bit of light left that makes it down to the ground, and we get reflections from the ground. So nothing's ever perfect. There is a little bit of finite range resolution due to the pulse width and timing jitter. So 20 centimeters is a good example number for the broadening of these, what would otherwise be very short peaks. And now I can roll the dice, and I can do a little simulation here of, if I fire my laser thousands of times, at what height or what range do I detect these photons? So these are single photons showing up. These are noise photons here. These are ones from the ground, from the canopy, and I can repeat this process many times and develop this, what we call a range histogram. Of course, we don't know what the black line was. We only know what we observed. And so we have digital signal processing algorithms that are designed to detect these peaks and figure out where the peaks are, remove noise so that we don't say there's any surfaces here in this middle area, that would be a false alarm or a noise point. It's also useful to estimate the relative reflectivity. And we can do that because we put down lots of photons and we count how many we got back. So you can infer the reflectivity in most cases. Okay, so that's how it works. That's how we go employ them. Let me just get practical here for a moment and show you our version of this LiDAR. So on the left, over here is a picture of this is our second generation prototype system. It's in a van, just a simple U-Haul van. We're carrying it from our lab across the street to the airport here at the Norwood Airport. It gives you a sense of how big this thing is. We carried it up the stairs into the aircraft, actually using these handles right here. And this is my colleague Chris looking at it there in the airplane. Here's another view of it. It gives you a sense of the size of these things. We have an optical bench, we have a laser, we have the detection system, scanning system, and a couple computers that record the data and control all the scanning. Just to give you a few more details, 100 kilogram type of mass on the sensor, a couple of kilowatts to run the system and to cool it and maintain the temperature correctly. We have it here on a spring mount. As you can imagine, vibration can cause problems. So we have an inertial navigation system, which with IMUs and gyros that measures the position and orientation, and being able to decouple the vibrations through the spring system is very helpful to get reliable data out of that. One of the things that we're particularly proud of has to do with our scanning. It turns out you can record lots of photons, but if you don't do that efficiently, if you don't design your collections efficiently, it's not too interesting. So like all LiDARs, we project a laser beam out of the aircraft, as I've said, and that laser beam is wide and illuminates many detectors, in our case, the 32 by 128 on the ground. Now we can scan that, we can point that kind of flashlight plus camera combination, think of your cell phone, we can scan it in both the across track and the along track directions, point it wherever we want, anywhere within 40 degree by 40 degree, what we call field of regard. So when it's time to actually go map an area, what we tend to do is divide it up into polygons, and I've shown that as squares in this example. And as we fly along, we can scan each of those polygons from multiple positions of the aircraft. Those multiple viewpoints allow us to look into nooks and crannies. It allows us to illuminate different sides of the buildings and also poke through holes in the foliage canopy. We do have it designed so it looks off to one side to be able to paint sides of buildings well, but of course that means we only paint one side. So we typically turn the aircraft around, fly the other direction, and then we can paint in the other side. Those squares or polygons are defined in geographic coordinates. So even if the airplane wiggles around, roll, pitch, or heading, or position, we still scan exactly where we intended to scan. So a real-time scan control system. Those polygons can be kind of arbitrarily shaped. They can be shifted. Here we can put in a dog leg like we did in this example, so that if we're following a power line corridor or something like that, we can accommodate that. Altogether, it makes for a very agile and efficient scanning system. I'll give you a few more technical details. It's a technical audience. I've mentioned the range resolution that comes from the pulse width, the width of the laser pulse, as well as timing jitter in the detector. And if we take all of those raw photo detection events, we have a full width half max of something like 18 centimeters. So about the width of your head. However, as we all know, looking at a shape like this, you can estimate where the center of that is. And average down. If you have a lot of detections, you can average down and get better precision, which is what this plot is showing. This is data over a big flat area, so we can divide that into smaller or larger, smaller meaning fewer hits, and larger meaning many more photo detections within an area, and estimate the height of that area of flat surface, and this shows our standard deviation. So averaging is working very well, as you would expect. Typical state-of-the-art requirements that people have are on the order of 3 to 10 centimeter RMS on measuring vertical surfaces for wide area mapping applications. So this works quite well. We make very good use of those few photons that we're getting. Here's a spec sheet of some of the major specifications of our systems. Zion A is a single camera system. Zion B is a 2-camera system. And I put this here just to kind of give you a sense of where the state of the art is. Range resolution, as I mentioned, on the order of 18 centimeters. On this second generation system with its 35-watt laser up here, we're able to have higher area collection rate and higher, and we also ended up with better timing resolution. The angular resolution, so the kind of optical point spread function, is 76 microradians full width half max. That corresponds to about 16 centimeters or so from 7,000 feet. So that means if there's, for example, 2 wires, power line wires or something like that, we can see that there are 2 of those as opposed to just 1, as long as they're wider than this 76 microradian separation. So altogether, all of these specs combine to say that we can map something like 600 square kilometers per hour at 7,000 feet and produce data density with 140 measurement points per square meter. So very capable for wide area mapping of urban areas, for example, or poking through foliage. I can walk you through a chart of how that works for other use cases. This is plotting the area collection rate that we can achieve as a function of the aircraft altitude. And each of these lines corresponds to a different data product density. So you can imagine, to get a 2-point per square meter product, I don't have to put down nearly as much laser energy per square meter on the ground, whereas, these higher point densities, I have to put down a lot, which means I have to narrow up my scan, fly slower, and that sort of thing. The takeaway from this is, for something like 100 or 200 points per square meter, which is the yellow and the orange lines, at 7,000 feet, we're talking about several hundred, 600 square kilometers per hour. So very capable of providing the input data that one might need for all kinds of analytics that you would want to run either on an urban area, maybe you're mapping a border, maybe you're doing disaster response applications and you want to, in an automated way, characterize what's the conditions on the ground. All right, so we've seen how it all works in terms of getting the data, and we saw a practical instantiation of this system. Now let's talk about processing a bit. And in some ways, with these Geiger-Mode single photon systems, that really is the second half of the LiDAR. So the raw data that comes in one way of portraying it sort of looks like this. Level 1 is what we call our raw data. There's a dot here in this 3-dimensional data viewer for every time that one of these avalanche photodiodes fired, every time we detected a photon. And we've adjusted our color bar so we're mostly focused on the area near the ground. And this kind of spidery structure is indicating that we collected from 4 different viewing angles. We scanned this area on the ground from these 4 different viewing angles. And we have about a 600-meter, what we call a range gator, or time during which the avalanche photodiode is active. So when you look in here, you say, yeah, there's something there, but boy, there's an awful lot of noise. So given all these raw measurements, the questions we're trying to answer are, first of all, where, meaning 3D position, where are the real surfaces as opposed to noise? So we're trying to get rid of noise and then locate the real surfaces. How reflective are they? And then we also like to report something about how confident we can be in that assessment that there's a real surface here. And there's some applications where very high confidence is important. Other applications where it's more important to be able to detect very faint signals and you can tolerate less confidence, more noise. Okay, so getting more specific, let's go back to our example where we look through the tree and we have this vertical histogram of, the amount of light we got as a function of height. And in this data collection, this is actually a reasonably typical collection that may have been designed to be able to image the ground. So get something on the order of 10 detections down near the ground. So again, where are the real surfaces and what's the noise? So the first thing that we might be tempted to do is to say, well, we can set a threshold, and anything below that threshold is noise. But let's understand sorry, I should have first said, let's understand the noise sources just a little bit. Briefly, there's three main sources of noise: intrinsic noise, or dark counts. So in the absence of anything else going on at a few kilohertz rates, all of these avalanche photodiode devices will fire falsely, thermal issues and so on. What that corresponds to, those few kilohertz, correspond to a probability of 1 in a million of having a false firing event per range resolution element, where our range resolution is, on the nanosecond scale. So that's great, very low. We can also have ambient light. So those are real detection events where there actually was light. But in typical scenarios with the F numbers and the photon detection efficiencies and the spectral width of the filters that we use, that ambient light is 0 at night to maybe tens of kilohertz during the day. So important, but not a huge deal. A larger problem tends to be crosstalk, meaning that when one pixel fires, there's a little tiny bit of photo emission, and there's some probability that some of its neighboring pixels, nearest neighbors or next nearest neighbors, or a few more out, can actually fire. It usually happens within a few nanoseconds. So there are ways to try to guess that something might have been a crosstalk event. But that tends to be the dominant noise source in these kinds of applications. All right, so we see the blue and we need to get rid of the noise and find the peaks. So one could set a threshold, as I was saying, like right here, and things that are small we get rid of. But a question is, where do I set that threshold? And maybe that threshold should be set differently at different points in this vertical distribution. So let's just simplify it. Let's model a very noisy set of observations where the probability of getting noise after all of these laser pulses in any one of these vertical bins, let's say that that probability is 15%. That's very high, but I made it high just to kind of accentuate what we're doing here. So it's Poisson statistics that describe the arrival of those noise points, as well as the signal points for that matter. And so I can plot up here, which is what I've done. I plotted up the distribution function for the probability of having, 0, 1, 2, and so on detections if my noise rate is 15%. So, clearly, if I put my green line here, I'm throwing away the 1 and the 0, but I'm not throwing away the 2 and higher. And so that means I have a false alarm rate or a false detection rate of something like 1%. May not be the end of the world, but that is pretty high. So you could take the green line and just move it to the right further and get rid of more noise, but there's a reason not to do that. You want to retain your signal. So the gray here is saying if I have an average signal, an expected number of photodetections of 5, then Poisson tells me that this is how these are distributed. And if I put my threshold at, between 1 and 2, now I'm not going to detect 0 or 1 points. So I'm going to have a probability of detection that's less than 100%. And so it's this balance between I want to have a high probability of detection, low false alarm rate. Where do I set my threshold, this green line here, in order to do that? So You may have heard of something called a receiver operating characteristic curve, or a ROC curve, which tells me what probability of detection I get as I make system trade-offs, and what probability of false alarm do I get. So in this line, I'd like you to focus just on this line here. This is for, I did the one set of measurements where my average number of detections is 10, but I can process that data with different thresholds. And so these green numbers here corresponds to different settings of my threshold. And I can sweep out, up here, I have a very high probability of detection, but I also have a high false alarm rate. And as you might imagine, as I move my threshold to higher values, I lose more of my signal, so my probability of surface detection goes down, but my false alarm rate also really goes down. We can work on a different curve if we had gone and collected our data differently. So these other lines correspond to different amounts of energy that I put on the ground effectively, or a different average number of photoelectrons that I've detected during my observation process. And I guess what I'd like to highlight here is that if I go from this line here, the kind of teal line, over to the green line, I've increased my investment in laser power, or the amount of time it took to do my measurements. I've increased that by 50%, which in some sense is not a huge investment. But I've been able to reduce my false alarm rate by many orders of magnitude if I'm working at the same, 99.9% probability of detection. So that's a pretty good bargain that, one doesn't often get in engineering. Our happy spot where we tend to operate these systems is over here, where our false alarm rates are quite low, kind of one fault surface in 1,000 by 1,000 by 1,000 voxel volume is one way to think about it. And a probability of finding things that are really there of, 99% or higher. All right. One comparison that one might make here is to the older technology, which we call linear mode LiDAR, where the detector is operated in a mode where its voltage output is linearly proportional to the instantaneous light input. So it's just a kind of a big amplifier right there. However, you're getting an RF signal out, so you have to have RF amplification, and there's noise associated with that. At the end of the day, the best, at least commercially available LiDAR systems built with those detectors require something like 300 photons coming in the aperture in order to have 95% probability of detection. With our systems, with this technology, we have 95% probability of detection with a 10 to the minus 11 false alarm rate with 30 photons coming in the aperture. The photon detection efficiency is about 30% on these devices, so this corresponds to 10 detected photons. I've said a lot of words. Hopefully I didn't lose you there, or if I did, this would be a good time to come back and we'll keep the story going. All right, let me say a few words about applications and why is this kind of LiDAR interesting. So as I've said, a lot lower signal requirement. We just said the 30 photons versus 300 photons. There's a physical reason for that. It's not magic. It has to do with the fact that we don't have RF amplifier circuits that add noise. They don't have to be these, gigahertz or multi-gigahertz RF amplifier bandwidths. So that's great. In a sense, we're putting the amplifier right in the photodiode in terms of this nonlinear, multi-volt drop that we see. It's a very nonlinear process, and the noise associated with that is just different. So I guess the reason why 10x lower signal requirement is useful is now I can work from a longer standoff distance, so I'm getting less light back, or I can have a smaller aperture, or I can have less laser power, less overall system power, less overall size, weight, and mass of these systems. Size, weight, and power, sorry. Size, mass, and power. All right. In some situations, you really have to detect very weak signals. And the noise that's associated with a linear mode avalanche photodiode is just too much. You're never going to see it. So you can work through an example. Here's one example. Suppose that the laser power that goes out and gets reflected from a surface and comes back and is captured by your telescope. Let's suppose that that corresponds to something like 10 to the minus 4 photons per laser pulse. With these detection systems, it turns out we can get 98% probability of detection with a, what I consider to be a very low false alarm rate, 6 times 10 to the minus 5, using 400,000 laser pulses. Now, that's a lot of laser pulses, but because of the noise properties of these detectors, we can aggregate up all of the detections that we got over the course of those 400,000 pulses and operate at this kind of probability detection of false alarm rate. So if you have very weak signals, imagine maybe, I don't know, you're ranging to an asteroid or something. That's a long way away. 1 over r squared is really bad. And or maybe you have a very small aperture. You just don't have much light to work with. This is a great way to make good use of very few photons.
Excuse me, I've got a question here, right here.
Yeah.
What's the typical pulse rate?
That's variable. We typically operate our systems, our airborne mapping systems, we're 50 to 90 kilohertz. It's related to the readout rates of the cameras. Obviously, you have to read out all the pixels, and there's certain bandwidth limitations there. There's other versions of these systems that allow, multiple 100 kilohertz, 200 to 500 kilohertz readout rates. Yeah, there's lots of varieties.
Just a reminder, please, Dale has asked that we put questions in the chat and that he finish his presentation before we get into discussion. So I appreciate it if you would accommodate him.
All right, thank you. We're almost done. All right, another thing that I find compelling about these systems is the high measurement rates. And I'm talking about just the number of the detected photons that we get per second. So we can use arrays of these avalanche photodiodes. And I mentioned 32 by 128 is commercially available. In the R&D world, 128 by 256 is in common use today. And there's really no reason not to make these substantially larger. And 90 kilohertz type of frame rates. So, yeah. And just as an example system, our second generation prototype system, our link, the amount of light we get back from the ground is typically 130 million photo detections per second at an altitude of 7,000 feet on a typical scene. So we're really scooping up the data very rapidly. One application of those kinds of high data rates is forestry. So when you have a forest, the first thing people like to do is get a sense of, well, how tall are the trees? So in order to do that, you have to say, where's the earth? Because you can easily measure the top of the tree, but where's the ground? So we need to be able to get enough data from under the trees to be able to create a digital terrain model of the ground under the trees. In this example here, this is some data actually we collected in Delaware recently. And you can see the ground is very well formed. I'll say a little bit more about it in a second. The next thing people like to know is like, well, how large in diameter are the tree trunks? How much lumber is there? Or how healthy are they? Are the branches developing well, or are they kind of stunted? Are the branches concentrated up high? How much of the tree is straight and you could cut into lumber? All those kinds of things go into lumber, the lumber industry. You also might have people who want to see what's going on under the trees. But for now, let me talk to you about this example. So this is the same data, both the top and the bottom here is the exact same point cloud What's different is in our data viewer, we turned a threshold knob having to do with the amount of signal. So we can crop each of these points that we have. We can crop based upon the height or the position or whatever, but also on the amount of light that we got back. So if I turn that knob from 3, which is saying kind of a bare minimum amount of light and maybe even a little bit of noise, as you can see here, as I turn that knob from 3 up to 10, now here I'm saying only the strongest returns are going to be retained in our point cloud. So that means that things like little small branches that intersected through the 10 centimeter voxel, those may not show up in this lower picture, as well as leaves may not show up either. This was the end of April, I think somewhere I said, no, it's not on here. Yeah, this was collected, sorry, the end of March. So it's partial leaf on, leaves are coming out. It's not fully foliated. And you can see here, there's a ditch where we have some data voids. That's due to water, standing water there that speculatively reflects the light away. Here's another ditch, and there's a big bump here and so on. So you can see here that by adjusting, this is just one knob that we're tuning here. You can sort of digitally defoliate and concentrate on the ground, or up here in the upper one, you can concentrate more on the branches and the tree trunks and that sort of thing. Here's some of that same data portrayed a little differently. So you can see the power lines in there, and you can see the ground. It's color-coded by the elevation. I'm going to next estimate where the ground is everywhere and then crop the data to within a meter or so of the ground. I've also recolored it by the height above ground. So you can see here's the post where the power lines had been. Let me go back. There's the power lines again. Okay. I don't know if that worked through Zoom or not. But when I now cut off all the trees and I see the tree stumps and I see the ground contour, one of the things that's interesting in this particular data collection is there's this kind of structure here of a berm, and we saw a whole bunch of these berms all over this area. And then we did a little looking around, research, and found out that it's an old World War II ammunition dump. So they actually had railroad tracks that went into each of these bunkers, and I assume there was some sort of a roof over top, and they stored ammunition here. I thought it was fascinating. You can also, once you've cut the trees off and you're looking down near the ground, you can see things like trails. So these trails, it look like were ATV trails where people get their 4-tracks and go zip around in here and go up over the berms. As you can imagine, that's probably a lot of fun. But you can see their trails going all over. Here's another trail over on this side. You can also see artifacts related to drainage. So there's either a ditch or a stream here. I think it's more of a ditch, and a corresponding one over on this side. And you can see, either somebody put a tree or a board or something across, so you could walk across the ditch from the power line corridor over to the playground over here. I would imagine there's a culvert, that goes under here. We've even in parking lots, you can see down into the manholes and measure how deep the manhole is, where the sediment is, and you can start to trace what the drainage patterns might be between the manholes in a parking area. So a lot of utility of this kind of foliage penetration data. Another example has to do with disaster response. And in particular, well, let me walk you through this example quickly. We're almost done. So here there was a tornado that came through New Orleans a couple of years ago now, and it followed approximately this red path. We went there very soon afterward and collected some 3D imagery. In this particular case, we see a house that looks like it's not on its foundation. Perhaps this is the foundation over here. This was data we collected Friday night, and then we collected again the next day, Saturday afternoon, and all that's left is a pile of rubble and a bulldozer. So what I'm hoping that you see here is we're able to do 3D change detection and volumetrics, meaning we can go measure now how much volume is in this rubble pile and provide some intel to someone who might be deploying, dump trucks to the area to pick up rubble. How big the trees are, how big of equipment you might need to pick things up. You can do automated analysis of all of these things, whereas other technologies might be less easy to do. In the interest of time, I'm going to skip this one. So I'll just conclude by saying, we talked about what LiDAR is in general, and we focused on single photon time of flight direct detection LiDAR. The range resolution of radar coupled with the optical resolution, or with the angular resolution of opticals, so the best of those two worlds. I talked about Geiger-Mode receivers in particular and how they work. We're detecting and time-stamping those individual photons, and we can do this with large arrays of digitizers, you might say. I showed you a couple of our products, so practical implementation of these Geiger-Mode systems with particular focus on airborne mapping. And what we get from those systems are these high rates of doing aerial surveys, 3D surveys. And just perspective, the area inside of Route 95 as it goes around Boston, the 128-95 loop, that's around 1,000 square kilometers. So if we're collecting data at many hundreds of square kilometers per hour, you could kind of scoop it all up in an afternoon. I talked through a little bit about the Geiger-Mode signal processing. We talked about the Poisson statistics and how you can, even after a data collection, you can go in and adjust your thresholding so that you can tailor make the probability of detection and the false alarm rate to match the needs of a particular analysis that you're trying to do. And oh, by the way, even with very low signals, we can still detect with high probability of detection and low false alarm rate. And then finally, we went through some examples of where this is being applied. Rapid collections of dense 3D surveys is the theme. Forestry analytics was one example. Imaging under foliage we talked about, and very rapid response over wide areas after disasters like hurricanes and floods and that sort of thing, to, in an automated way, inform the job of first responders and recovery people. So thank you for your attention very much. And with that, I will stop and go take a look at the chat.
There were two people in the audience here that had questions with no access to chat. So I'm going to take the privilege of letting them ask their questions first before we get into that, with apologies to the people who have paid attention to the rules. Go ahead, Jerry.
How do you establish the position of the LiDAR equipment in the airplane? With what accuracy?
Could you hear that?
I did. And that's a great question. It's fundamental. So it turns out that the state of the art for GPS systems tightly coupled with accelerometers and gyroscopes, whether they're MEMS gyroscopes or ring gyroscopes, those systems give us, over short term, they give us positional accuracy on the order of a handful of centimeters, and they give us angular accuracy that supports, the level I was talking about here and even better. Over longer term, the absolute is still quite impressive. So we have a GPS antenna on the roof. We have the inertial measurement system or inertial measurement unit on the optical bench itself. And then the state-of-the-art software for doing a Kalman filter to get the best estimate of your position, simultaneous position and orientation. That software is very good. And we basically turn the crank on commercial software to get that answer.
Good. A question about applications, the ability to see a difference in your target area. Has anybody thought about this or pitched it to a government agency in terms of monitoring the effect of climate change on vegetation?
I don't have firsthand familiarity with pitching that idea, and that's a good one. I think things like
He's looking for a job as a salesman, so you just talk to him afterwards.
all right, sounds good. No, but people are certainly the lumber companies and the people who harvest their forests are very interested in growth rates. And so they will do things like measure year over year how much growth they had, vertical growth as well as radial growth of trees, and quantify that. And so I'd imagine that, you know, the technology is there to correlate that to climate, what happened climate-wise during that past year.
Any other questions here?
Yeah,
Yeah, one more.
I've seen reference to LiDAR being used in archaeology to look over areas that they had no idea, like in Mexico is this the same technique, or maybe not as accurate, but would this be applicable to that?
Absolutely. And I apologize. I should have mentioned that application in the, you know, looking through foliage part. That's a very good point. And I apologize for missing that. Yes, this is exactly the technology that's used for that. The LiDAR technology is. People have done a great job with some of the older systems that aren't as fast. You just go fly slower and take more time, but you can still see down to the ground. Having the analytic algorithms that allow you to estimate where the ground layer is and cut away the foliage, you know, there's a lot of work that goes into making those work reliably. But yes, this is exactly the same, you know, time of flight, direct detection LiDAR is airborne LiDAR is what has led to those discoveries. It's really exciting.
Thank you.
Should we start going through the listed questions here?
Yeah, do you want me to read them to you, Dale, or you have them in front of you, and you can do it? What do you choose?
I have them in front of me. I figured out how to get the window open. So yes, I can read them. So the first one, do you take into account difference in the speed of light through air and water? Yes. And it is important to, you know, figure out what the index of refraction is through the air column on the day you're doing the measurements. It turns out for the accuracy that we're typically looking for, the index of refraction doesn't change enough on a day-to-day basis to cause a problem. Our systems at the wavelength that we are using, 1064 nanometers, they don't propagate through water more than a centimeter or two. But there are bathymetric LiDARs that are in the visible, that are in green and blue, that do, and they use them to go down quite a ways through the water, you know, several what they call Secchi depths, which has to do with the turbulence and scattering in the water. And so, yes, they have to think very carefully about the index of refraction through the water, as well as the angle of the water surface and refraction that you get as you go in there. So yes, that you're onto a very important point. The next one, can the mapping collect real-time events, such as seeing people walking or vehicles as they move? Yes, absolutely. We do that on a regular basis, sometimes on purpose, but usually inadvertently. It often happens if you're scanning an area where there's a highway and people are driving along, you'll get multiple images of the same vehicle as you scan that section of highway from different angles or different positions of the aircraft. What's important is it's different times and the target has moved. So yes, absolutely. You can get the speed, or like boats on water. Yeah. What's the price range of the cameras that BAE sells? Well, as you might know, we have NDAs with them, but let me just say they're not cheap. Not at all cheap. Yeah. Okay, as the plane is moving and as it's doing the mapping, the sending laser beams to a given spot on the ground, can the laser angles see under objects? Yes. Oh, I just answered yes. Okay, good. Can you in any way measure what is under the ground, like bombs or tunnels? With this technology, it's only where the light can propagate, that we can only interrogate surfaces that the light can get to. However, you know, there are indirect things that you can do. I know there actually have been efforts to vibrate the ground in some way, acoustically or otherwise, and then look at the response, the motional response of the ground in order to search for IEDs, buried IEDs. It's really fascinating work. I know some of my colleagues at Lincoln Lab have worked on that and have had some pretty good results with that. So it requires some sort of excitation, and then, like acoustic or seismic of some sort. But then you can do laser vibrometry to measure the response of the ground to that impulse or that tone that you've given it. So there is some of that that goes on. I don't have a clearance at this point. I don't know, I'm sure there's all kinds of super interesting things that people do that I'm not aware of. And if I were, I couldn't talk about. Can you damage the eyes of observers on the ground? No. You will be happy to know no. So yes, one could if you didn't design or operate the system correctly. We are very careful about that. And the eye safety regimen that we follow, which I believe is more stringent than a lot of our competitors, because we don't need as much light, we plan for an observer on the ground using large binoculars, staring at the airplane at the same time that the LiDAR is pointed for 10 seconds at the person on the ground who's staring at us. So if you put all those things together, and you're at our minimum altitude, you're still not damaging the person's eyes on the ground. So usually, it's a scanning system, so it's an intermittent exposure. Usually the people on the ground aren't using binoculars, but they might if they're curious what the aircraft is. And we usually don't stare at the person, and we are always higher than our minimum safe altitude. So great question. And the single photon technology makes it easier to be eye safe because you need less energy deposited on the ground. Okay, I think I did that one. How do you get the tilt data? Not quite sure what that one's referring to.
Dick, you want to explain your question?
Yeah, you mentioned that when you can do direct imaging, you can look straight down, straight up and stuff like that. But in passing, you said you would get tilt data, say, on one side of the buildings, and then you would come back again and get tilt data from the other side of the buildings. And I'm wondering how you actually generate that tilt data, or probably how you detect and then analyze it.
Yeah, thank you. Thanks for clarifying that. So I may have been mumbling or talking quickly there, but so in our particular implementation of our sensors, which is not what everybody does, but we've chosen to kind of bias it or aim it, tilt it off to the side so that we scan from about vertical to about 35 degrees. And what that enables us to do is get the sides of buildings, illuminate the sides of the buildings well. So that was the tilt I was talking about, was the sensor itself is tilted. Obviously, we know what the tilt is because of our GPS and our inertial measurement unit. But the idea is to set up the collection so that we're illuminating the sides of buildings and we can then get those. And then because it's only getting one side, then we turn around and we fly the other way and get the other side.
Great, thanks.
Yeah, no, good question. Wavelengths, so the systems that 3DEO, my company, works with today are 1064. We've also done work with 1550. The LiDAR industry in general, it's, the usual suspects: green, 532, which is doubled 1064, and 1550 or thereabouts, so that you can put down more power on the ground and still be eye safe. So it's really 532, 1064, and 1550. There are some LiDARs where you're trying to look through more of the atmosphere, so you're more worried about atmospheric attenuation, where they're working at 2 microns. There's also ones for looking underwater that are more like bluish, so in the 400s, high 400s. And then there's the super continuum lasers that some people use. So you have a pulse that's very wide, maybe even up to an octave of optical frequencies, so that you can do hyperspectral LiDAR. So you kind of have range resolved hyperspectral. So people are creative and do lots of really interesting things. Let's see. Next one. Do you use different laser wavelengths for different conditions? You could. or multiple wavelengths at the same time? Yes. One of the things that's kind of cool about multiple wavelengths in the foliage penetration application is that when you're looking through canopy, you have the same obscuration fraction for both wavelengths at the same time. And so you can look at the relative ratio of light reflected from a surface and get a sense of, yeah, this is this kind of material or this other kind of material based upon the relative reflectivity at those 2 or 3 or 4 wavelengths. And that's it's useful to do, especially in that foliage penetration application, where you have the same obscurations and you're therefore able to do the math better. All right. So that's one example. So material identification. Is the laser or lasers you use, could they be weaponized, i.e. see the bad guy running through the forest and disable him? I suppose. That's not the business we're in. I was approached once by somebody who wanted to use the lasers to kill certain plants. We decided not to do that because that just sounded like a real nightmare in terms of liability and hitting the wrong people. Yeah, I would imagine. Certainly, you know, CW lasers are used for taking down drones. So those are up in the air flying. I think the Navy has big programs on that. Find lost hikers in the mountains. I would love to. I think one way that the problem here is clutter. So by clutter, I mean other objects of about the same size that look sort of like your hiker. So one way you could do this, I don't think it's really affordable, would be to cover the entire area that you might one day want to search. Go Lidar the whole thing and get your point cloud of what we call the human activity layer, that stuff near the ground, what that looks like. And then when someone's lost, you could go do it again and you could do geometric change detection, look for changes in the geometry of the scene. That I don't think is a good idea. But that would be one approach. Yeah. And can the heat of the object be measured? Yeah, you could get a thermal camera or something like that, but then not clear why you would need LiDAR. It's probably better just to use the thermal camera. But yeah, no, good ideas.
Yeah,
Any
just
other
one-
questions?
Yeah, just one thing from here. If someone wanted to do a geodesy from space, is this technology applicable to something like that? You alluded to asteroids at one point in your presentation. Is any of this stuff applicable? And are, you know, without going into things you don't want to talk about, you know, is there a realistic chance it might be employed?
I think depending on the precision you were trying to get to, maybe, but it's probably not the right tool for the job. I think so geodesy is like looking at very long baselines and the movement between continents. I think I'm understanding correctly what you're asking about,
Yeah.
or like vertical and horizontal movement.
Right.
I think that probably just the RF GPS receivers are probably the best way to do that. It's been amazing what the space-based LIGO project is doing. I'm certainly no expert on that, but they've been able to do some pretty amazing optical interferometry. So in the space vehicle to space vehicle connection, if you wanted to measure some distances there, yeah, optical would be a great way to do that because you can put the power right where you want it. Going down through the atmosphere, there are other considerations there of the distortion going through the atmosphere. So I'm not sure if it's the right solution for that problem or not.
Yeah, the reason I think about it is that recently, last week, I think they talked about the sinking rate of the Earth's surface in some of the areas. And I assume that this is the kind of technology they use to measure those kinds of things and to understand what was going on.
It might very well be, or it may also be that you know, if you have a network of GPS receivers, you know, base stations that are they're called continuously operating recording stations or core stations that are used as part of the kind of the national infrastructure for survey. They're basically GPS antennas that are anchored to one spot and just keep recording for a very long time. You can average down your random noise very well with those. And so it may be that they use those. I'm not sure. I know
Yeah.
there is a company, very recently funded startup company, whose goal is to do 3D LiDAR mapping from space. You know, they're limited by the power and aperture that they can use. So, you know, they have to choose carefully what questions they're trying to answer. But it's certainly doable with this kind of technology.
And the other thing that came to mind when you were talking is going through water. You know, you don't do it, but using technology like this, I'm going to use the wrong word out of ignorance here, so just bear with me. Is it thermoclines where you have different layers of the water that are different temperatures that in fact causes sonar aberrations when you're using that? Is that the right word? But that's the technique. That's what I'm trying to describe. And do you account for those kinds of things, or can you account for those kinds of things in doing submarine, if you will, being below the water investigations?
I would imagine you could. I'm certainly not an expert on that, so I don't want to embarrass myself too badly. But I think underwater, what you are often up against is the random scattering. So you get return the light power coming back at my detector is, first of all, you have backscattering from multiple distances, but you can range gate that out. Then the next thing you have is, even if you did get your pulse out to an object some distance away, the light going out there has taken many paths because of small angle forward scattering, and the light coming back likewise has taken a lot of paths, which tends to distribute the signal both in range as well as in angle. So it's what you see when you're in the swimming pool and things kind of look blurry if you have your goggles on, right? But things still look blurry at longer distances away. So it is an issue that they have to deal with if you're looking at those longer distances.
Do you have the same issue with going through the atmosphere, or you're flying low enough that it's minimized?
If you can imagine, if you're looking straight down, then you get no angular deviation. You get a little bit of a range shift, but no angular deviation. It's when you're looking way off to the side that you get some angular deviation, because it's kind of like a little bit of a lensing effect. You have those gradients of the index of refraction. Yeah, so people have studied how much that bending is, and as long as you have a decent model for the vertical distribution of the index of refraction based on the chemistry and temperature and so on, then you can there's codes out there for correcting for that.
Is that part of the reason why you limit the width, the angular width that you survey?
No, it's that for a lot of applications, at least for our systems where you're using them in a permissive airspace, you can put your airplane wherever you want it. Then first of all, there's shorter distance if you're measuring vertically, so you don't, your laser doesn't have to be as big. And second of all, often what you're actually looking for, you're more interested in horizontal surfaces, the ground, a rooftop, things like that. You're more interested in that than like sidewalls of buildings often, because you're trying to measure, gravity is the symmetry breaker, and you're looking at things like structures, a house or a shelter in the forest, or some wires that are suspended, or drainage patterns, all things related to horizontal or nearly horizontal surfaces. So it's actually better to look straight down. You also have less shadowing if you're looking kind of, walls tend to be vertical. So if you're looking parallel to those walls, you have less shadowing. If you're looking at from the side, then, you get lots of shadowing problems.
Good, thank you. Thank you. Sorry to monopolize a little bit. We still have 15 minutes of time if Dale is still available. Any other questions for him on Anything he might know about, we can do a trivia test with him. Yep, you got one more.
Just a quick, another application question.
Well, I don't have a question, but I do have a comment.
David, just 1 second, please. We have
Okay.
one here, and then I'm happy to call on you, please.
Okay.
Do you think it is possible or useful to base one of these LiDAR systems on a dirigible so you can cover an area over a long period of time and continuously collect?
Absolutely, yes.
See, I told you there was a sales guy in the audience. David, go ahead.
You know, I was just thinking, listening to you, you know, I like to watch Josh Gates, the archaeologist who goes all around, but especially down in South America, you know, and even in the Isthmus, the stuff they have found in the forests down there is amazing about the culture. You know,
It is.
I mean, I'll tell you the truth. If the kids today in the future, when they're going to be an archaeologist, boy, they got a lot of beautiful tools to use, and you're part of it.
Thanks. Yeah, it's exciting to be part of that. Yeah. Yep.
Any other questions? Anything else that we can ask Dale?
I have a couple of comments. I've just been experimenting here with my iPhone, and I have an iPhone 14, so it has a LiDAR button on the back of it.
Yep.
You know, this is pretty much a toy compared to the stuff that you're doing, but are these likely to get better? What's I know there's a big difference between this one and the one you are doing, but explain what some of the differences are and how this thing is actually working.
Well, of course, Apple's very tight-lipped about exactly how it works, but my understanding is that those are actually single photon avalanche diodes. So the same kind of Geiger-Mode diodes. I believe the readout is a little bit different. It's not necessarily time stamping every photon. I believe it's kind of binning photons up on the chip itself. So there are similarities there that it is working kind of at the single photon level and at least starting there. You know, obviously the difference is there's a whole lot less laser power. It's eye safe at the aperture. It also does not have the precision scanning system that we have. So I kind of glossed over it, but currently state of the art on these cameras that we buy, they're 32 by 128 pixels. So obviously, how do you make an image like this image of Boston from, you know, a 32 by 128 camera? And the answer is that you very carefully scan it. Now, with the iPhone, you can take your phone and just kind of pan it around, and there's some really good software in there that stitches together a 3D representation of the scene based upon its best guess of how you were moving it, plus the imagery and registering individual snapshots together. So you can do some scanning, but having, you know, kind of wide angle, very precise scanning and fast scanning is something that, you know, these airborne systems have to address. So laser power, scanning, and then the GPS and the inertial measurement unit, IMU, tend to be much more precise. And then the way we record the data, you know, we do our raw data is these individual photon detections, and then in post-processing we can throw lots of different algorithms at them that take a lot of CPU time, frankly. It is possible to process the data in real time, but you know, you're not going to do it on an iPhone. So with the iPhone, they have by necessity had to simplify a lot of the processing that they do, which is fine for, you know, what a lot of people need. That's perfectly fine. But those I would say would be the big differences.
Great, thank you.
Yeah.
So basically, I shouldn't go out and buy 10,000 iPhones and stitch them together.
No, it's tempting to think about that. The other one is like you go down to Lowe's or Home Depot and get you know 1,000 of the laser distance meters, right? You can get those as well, which is it's a little LiDAR there. But they do one measurement or maybe 10 measurements a second, and at much reduced range, obviously.
See, you spent all this money, all this time, got a fancy degree, and you got some guy that goes to Home Depot and builds the same thing for $400.
Right.
maybe, it might even work.
It's, you know, it's good enough to the nearest 2 miles, you know, what the heck?
Yeah.
I think that was an excellent presentation.
Yeah.
because we pretty much
Thank you again.
pretty much
Thank you.
did it.